Now let us discuss about rotating coil in a magnetic field. Rotating coil. Rotating coil in a magnetic field. Suppose in a magnetic field, suppose we have a magnetic field. This is the magnetic field B in this direction. And we have a coil here with n number of turns. This is a coil and having n number of turns. So this coil has n number of turns and it is rotating with angular velocity. It is rotating with angular velocity, suppose omega. It is rotating with angular velocity, suppose omega, right? So now here you see this is the magnetic field B and its angle made by its area vector, suppose this in this direction, angle made by area vector d theta in time t, sorry theta, angle made by this area vector with magnetic field B, suppose in time t be theta, okay. Then its angular velocity will be omega will be equal to theta by dt, which implies that theta is equal to omega t, right? Now magnetic flux phi is given by, we know that B vector dot A vector. A is area vector, B vector is the magnetic field, right? And dot product of these two vectors is BA cos theta, okay. And this theta is here in this case omega t. Theta is omega t. Just put here. Then what you will get? BA cos omega t, right? Now EMF induced in this coil, EMF induced in this coil, E is equal to, we know, as there are n number of turns in this coil, so it must be minus n d phi by dt, right? Now here you see so here n is equal to number of turns in the coil. In the coil. Remember it. So that's why this n comes here. So now minus n d by dt of phi is nothing but BA cos omega t. BA cos omega t. Right. So this is what? EMF. Okay. Now here you see one more thing, that in this case this area, in this case area and magnetic both are fixed, so we can write this area is fixed here, it is not changing, and area vector is the angle between the area vector and magnetic field is changing with time. So here cos omega t is the function of time only, here is dt, so that's why E minus n can then be a d by dt of cos omega t, cos omega t. Now you see in differentiation, in mathematics you have to learn differentiation, right? So we know ddx of cos ax, if a is a constant, is constant. Then we know derivative of cos x. Derivative of cos x is minus sin x, right? Minus sin x. If there is cos ax instead of cos x, if there is cos ax, then it will be minus a sin ax. This is function of x and we are differentiating with respect to x. So here it is function of t and differentiating with respect to t. So that's why. So here instead of a we have omega here. So that's why minus m b a d, sorry, derivative of this will be minus sin minus omega sin omega t, right? Omega t. That's what we will get. So now here you see at the end, as the final result is, so this is minus plus nba omega sin omega t. So this is the EMF induced in this coil rotating in a magnetic field. Now here you see, let me clean this part. We know that maximum value of sine function, is 1 plus 1, right? So therefore this EMF will be maximum if sin omega t is 1. So maximum EMF, let it be denoted by E naught. Maximum EMF we will get when we will get maximum EMF when sin omega t is equal to 1. So that's why if this sin omega t is 1, then maximum EMF will be nb omega, right? Sorry, nba omega. This one will be the maximum EMF, right? Because maximum value of sine function is 1. So that's why if you put here 1, then you will get the maximum EMF. So we can write this expression. We can rewrite this expression as, we can replace this sine nba omega by this E naught, because E naught is equal to nba omega, right? So we can write induced EMF E is equal to E naught sin omega t, right? So this expression can be written this way, where E naught is equal to maximum EMF nba. So hope you have understood. Now let us discuss about eddy current, right? Now let us discuss about eddy current. So now we know that when magnetic flux changes across a coil, maybe in this shape or a rectangular shape or circular shape, whatever, if magnetic flux changes across these coils, then what happens? EMF is induced here, and that's why current also induced current, right? Now instead of a coil, if magnetic flux changes, these are magnetic field lines, and those magnetic field lines changes across a solid body, a conducting body, then the current induced in that body will be called eddy current. Okay. So let me write the definition here. So what is eddy current? Okay, it is nothing but it is the induced current due to change in magnetic flux in a conducting body. So this is called eddy current, right? Now, so induced current in this case also it is given by E is equal to minus d phi by dt. Okay. So when we say body, there is no number of terms that's why we can directly write E is equal to minus d phi by dt. This is the induced EMF, induced EMF, and current will be given by I equal to E by R. That's going to be minus 1 by R into d phi by dt, right? So now here you see the direction of eddy current is can be determined by Lenz's law. Now let us consider a metal plate. This is a metal plate. This is not a coil. This is a metal plate, and this is and here, and it is allowed to oscillate. Suppose I have strike this and it is allowed to oscillate. Then it will oscillate this way, and due to air resistance, after a few minutes, it will be again at rest. Right? Now let us consider another condition. Suppose this is the north pole and this is the south pole, and magnetic field emerges from north and merges at south. This is the direction of magnetic field, right? So let us keep the same plate, metal plate here. These are the magnetic field lines, and plate is kept here like this way, and it is allowed to oscillate. In this case, it will take less time, comparatively less time to come at rest compared to this. If we oscillate applying the same force in both cases, it will take less time to come at rest. Okay. Because here you see, when it will oscillate in this direction, it will oscillate. This is the magnetic field lines in this direction. If this comes, if the plate oscillates like this, then what will happen? This red color is the north pole, suppose, of the magnet. If it's when the plate is coming to this direction, oscillating in this direction, then what will happen? According to Lenz's law, the induced EMF produced here will oppose the cause of production. So while it is coming to this direction towards you, then the eddy current produced here. This induced current will be called eddy current here. That eddy current will resist coming towards this. That means direction will be towards both. That will be the direction of the eddy current. And as it is not pole, to resist this plate going to this side, going away from the pole, this face of the plate should appears as south pole. Then this north pole will attract itself to resist it, and when it comes close, then again this plate, this face of the plate will appears as north pole. Then this will repel to resist to coming towards itself, towards the north pole. Hope you have understood this. So that's why this eddy current, the eddy current creates a retardation. Retardation means opposite of acceleration, negative acceleration, you can say. And that's why it comes to rest soon, very soon, compared to this one, in very less time. Okay. So that means what happens? Eddy current produce retardation, isn't it? Retardate. that means negative acceleration. Eddy current causes retardation, and also because of retardation, and as this eddy current oppose the cause, and there will be a loss of energy in the form of heat. Okay. So now to overcome this retardation and heat loss and to minimize the eddy current, what we can do? This metal plate, we can make holes. Then this eddy current will be discontinued, and then retardation will be less and less heat loss, right? And if you place a solid body, suppose like this box type body, so what will happen? In order to reduce the eddy current here, then what we will do? Instead of this solid box, we will use another such solid. Instead of this solid, we will use such a solid which is made of many plates and separated by insulating materials. Then also we can minimize this eddy current heat loss. Okay. So using the property of this eddy current, we can use this principle, and we can use this eddy current in magnetic brakes which are used in bullet trains, and as eddy current also produce heat, that's why it can be used in induction cooker. Okay. Those are the use of this eddy current. So hope you have understood this topic. So in the next video I will come up with another topic.